problem statement, two recursion approaches to find the sum of all numbers. We use two recursion approaches to find the sum of all the numbers in a nested table, right? So this is our first approach. This is return based approach. This is the table. As you can see, there are many tables. There in tables is our table. There are string values and there is boolean values. So as you can see, we create a local function to find some item, and we give local sum equals to 0. So every recursion call creates its own local sum, right? So each function call has its own separate small answers, and then you can say with the type item equals to number. If it's a number, then print it, and of course return item. Why this? Return item. This is our base case. So if the item is already number, then there is nothing more to search, right? If it's number, then we don't need to search. So I simply return I simply return that number, right? So the recursion stops. Then again, if it's a table, then we use a table. If it's a table, then we use for loop to find the items inside of table. And yes, and look at this. This is the important part. Sum equals to sum plus find some value. So what it does, it is recursively processes the values. So if the value is number, it returns numbers, right? It will return the number here. And if the value is table, it goes deeper. If the value is like table, it will go deeper, right? And eventually return the sum of, right? Like here it is 1, 2, 3 and 4. And if it's a table, so it will do the sum of all this, and like the sum will be 10, and then return to the table and return the sum of all numbers inside the nested table. So this table's value will become 10, and if anything left here, right, let's suppose here is 1, so this will become 10, and of course the base numbers which were present in the first table, it will be added to the right. So the value of this table becomes this, right? It's just an example, right? So of course then I return all the current values to my sum. So after all the values inside the table having processed, I return the total sum for the function call. Again, I just run the function again of this my table. So it prints the table right here because of this number. If it's a number, then print. So if it prints the table and also prints the total, right? So let's see the summary of this approach. So to summarize the first approach, if item is a number, returns it. Right here it returns it. If it's a number, it returns it. If item is a table, recursively get the sum of each child. If it's a table, then recursively get the sum of each child, right? And return the final sum. Here return the final sum. So this is called return based recursive approach, because every call returns its own contribution upward. So this was our table 1. We'll move to table 2. So in this method, as you can see, we have created two parameters inside of function. One is the item and another is the sum. Last time it was only one parameter, that was item, and we created this local variable sum. So it keeps updating it. It keeps adding all the here. It keeps all the tables inside of the nested table, then prints the final sum. But here we are adding another parameter here, that is sum. So as you can see, here we take two parameters, that is sum and item, right? But in the first one we only took one parameter, that was item. So of course the sum is passed as a function, and we put this right here. Sum equal to sum order. This ensures that sum starts at 0, right? This will ensure that sum starts only with 0, right? If the sum is nil, then make it 0. If the total sum is nil, then it will make it 0. So when I call the function for the first time without giving a second value, it will automatically start from 0. So yeah, then again it's the same thing. If it's a number, then print the number. Why we are printing this? For this table. Why we are printing this item? For this table here. Then look at this. Return sum plus item. So in the first method, you can see when I found the number, I returned only the number itself. Here I return sum plus item. This means that I am not returning just the contribution of this item. I'm returning the updated running totals, right? Here the totals are updated, right? So that's what I'm returning. Start. So again, if it's a table, then we'll use this for loop to find the items inside of the table, and then I will use the recursion here, find some value sum, and we run this sum function here again. So I pass this current sum into the recursive call. Then the recursive call processes that value and returns an updated sum, right? Here the updated sum, and that updated sum back into the sum. So instead of collecting small answers, adding it right here, it was doing like here, it was collecting the small answers, then 10 plus whatever it's 10 plus it, that's 19. So instead of collecting small answers, right, then it pluses later and later, and then updates. And so here, instead of collecting small and adding them later, what we'll do is this methods we keep carrying one running total forward, right? It's like all of the total forward through all recursive calls. Every recursive call, this sum gets updated, right? But here we add the sum later on. We add the sum later on, return the sum, but here everything keeps getting updated. So after all values are processed, I return the final running total. So of course we print it and the total sum is given. So let's look at this summary of the second approach. So what we here do is pass the current sum into recursion, right? Update it while moving through the structure. We keep on updating it as the recursion goes on. Return the updated sum each time, right? Every time the updated sum. So this is an accumulator style approach because one running total is passed through recursive calls. So those are both the methods. So let's compare them. So as you can see, we have made a table to compare them. This is the feature, this is method 1, this is method 2. So as you can see, this is our main idea. This method 1 is each recursive call returns its own answer. So there, every table we were getting the sum of every table, but here one running total is passed and updated. We use the sum as parameter, so just that function parameter sum was getting updated. So the number case, it returns only numbers, but it returns sum plus item. As you can see here, it returns sum plus item. So table will get sum for each child and then adds them. So there were many tables, right? Table inside of table. It's all tables. Table 1, it is table 2, it is table 3. So it was so when the recursion was called, each child of this table was getting getting added, and then every child here was getting added, and then so this is how recursion works, right? Especially in our first case, this was our first case. as you can see here, every 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 table was getting added here, if you can see. But here in this second case, passes sum to the children and keeps updating them. It just passes the sum to the children and it just keeps updating them. Here we need to, right, here we need, if you see, we need to in the end we needed to do this addition here, but here it just keeps getting updated. Because of that, we added this sum function as a parameter. So readability, this, it is clean and easy to understand, but it is slightly complex and harder to follow. The mental mode, solve small problems and returns answer. So every recursion solves their own tables and then it returns the answers, but it keep modifying one shared variable, and that was sum. Of course, it's pretty straightforward. This, the first version, it was pretty straightforward, but the second version, this, it was not that straightforward. You know, the sum keeps changing across all the calls whenever a recursion is called. So the sum keeps updating it, right? So this is classic recursion. Here, divide and then combine. But in the second version, it's accumulator forward state. This learning value, first one was best for beginners, the second one is better for advanced understanding. So yeah, this was our video. Thank you.